Okay, this is a really annoying problem. So we have a charge at the center of this four-particle charge arrangement, and we're looking for the net electric field at that center point from the surrounding four charges. The reason why this problem is so annoying is because not only do we have four different particles to work with, but since we're looking for those four particles' impacts on a central point, that means that every single force line or electric field line will be at an angle. And remember that when we have vectors at an angle, we can't really do direct math with them until we break those angles up into a x and y coordinate, the horizontal and vertical components. So technically, for this problem, we'll actually need to use the Coulomb equation 8 times in order to solve this. Fortunately, though, you have your fearless leader to guide you through it, and there are a few ways we can make this a little easier on ourselves. First, let's make a note of the signs of each charge. So it says Q1 is positive 10 nanocoulombs, so Q1 is a positive charge, Q2 is negative, Q3 is positive, and Q4 is negative. One thing that'll help us out a lot with this problem is understanding the concept of symmetry and how some electric forces can cancel each other out if they're pointing in opposite directions. For example, let's take a look at charges Q1 and Q3. Remember that electric field lines point away from positive charges and towards negative charges. So the charge from Q1 will be pointing away from the particle because it's positively charged. So at the central point P, there's going to be an electric field line coming down and to the right towards Q3. And since Q3 is also positively charged, Q3 will have its own electric field lines pointing away from that particle, which at the central point will be towards Q1. So we've got two vectors pointing in the opposite direction, which means there is going to be some extent to which those forces are going to be canceling each other out. Some of those electric effects will cancel out. And it's actually not hard to figure out just how much will be canceled out. So according to the problem, Q1 has a charge magnitude of 10 nanocoulombs, and Q3 has a charge of 20 nanocoulombs. Now, if charges 1 and 3 had the exact same charge magnitude, then their electric effects would be equal. They would cancel each other out perfectly, and we could basically just ignore Q1 and Q3 entirely. But in this case, since Q3 has a greater charge than Q1, that means that there is an excess at charge 3 if we want to try and cancel some things out. But that still helps us, because we can still imagine that these 10 nanocoulombs from charge 1 are being cancelled out by 10 of the nanocoulombs from charge 3. So, if we assume that the charge from Q1 is being cancelled out by some of the charge from Q3, then that means that this system is the equivalent of if Q1 was just not there, and instead, in Q3's position, we just had a charge with the magnitude of 10 nanocoulombs. I hope my explanation on that made sense, but the point is that we just simplified the system somewhat, because now we just don't even have to worry about what charge 1 is doing, because we found another way to accurately represent the system without charge 1, and by lowering the charge of charge 3. Now let's do the same thing for charges 2 and 4, because charges 2 and 4 are both negatively charged. And remember that according to convention, negative charges are where electric fields end. So for charge 2, for example, charges are going to be going into charge 2. The electric field lines are going into charge 2. So at the central point, there's an electric field line going towards the top right. And from charge 4, again, the electric field lines are ending at the charge. So from the central point due to charge 4, there is an electric field line pointing to the bottom left. So those two charges are also going to be canceling each other out somewhat. And according to the problem, charge 2 has a magnitude of negative 20 nanocoulombs, and charge 4 has a magnitude of negative 10 nanocoulombs. Now, just like what we did with charges 1 and 3, we can see that 10 of these nanocoulombs are being cancelled out against the 20 nanocoulombs from charge 2. Which means that in our simplified system on the right, we can just ignore charge 4 entirely and instead represent charge 3 as a particle that has a charge of negative 10 coulombs, or negative 10 nanocoulombs. And so just like that, we've created a much less intimidating version of the system that's still going to be accurate to our final answer. So now that we've simplified the system, we're finally ready to start doing some math. Recall that the electric field, due to a point charge, is equal to the Coulomb constant multiplied by the magnitude of the charge producing the electric field, divided by the square of the distance between the charge and the point we're analyzing. Let's first find a formula for this r. Now, because of the way this problem is symmetrical, that r value is going to be the same for every single point charge. It's just the distance between one of the charges and the central point. And we can find that distance by using the Pythagorean theorem. Because we're told that the side lengths of the squares are a, we can use the Pythagorean theorem to find the distance between two of the diagonal charges, treating that like the hypotenuse of a triangle. So, remember the Pythagorean theorem says that the squares of the legs added together are equal to the square of the hypotenuse. So in this problem, that is equal to a squared plus a squared, so 2a squared, is equal to the hypotenuse squared, it's just the square of this distance. So taking the square root of that, the square root of 2a squared, we can just take out the a, so that is a times the square root of 2. So the distance between two of the diagonal lines is a times the square root of 2, but if we're actually looking for the distance between the central point and the point charge, we actually need to divide that by 2. So the actual distance, r, is going to be equal to a times the square root of 2 divided by 2, because we're halving it. So our electric field formula will actually be represented as being divided by the square of a radical 2 divided by 2. And this is obviously a really messy and scary way to write this, so let's add the squares. This becomes a squared times radical 2 squared, which is just 2, divided by 2 squared, which is 4, and then we'll bring this 4 into the numerator. So this is 4kq divided by a squared multiplied by 2. And the 4 can divide into the 2, so that it's just 2kq divided by a squared. Okay, I know that was a lot of steps to get to that, but we now have the form that we'll be using for the electric field for each of the two charges. Because the electric field is a vector, let's sum up the components from the charges in both the x and the y coordinates. So the net electric field in the x direction is going to be equal to the sum of the components from the electric field for the two charges we've simplified, charge 2 and charge 3. So first off, from charge 2, even though charge 2 has a negative sign, the x component of the electric force is actually going to be positive because we can see that the x component of the electric field vector that's being created is pointing to the right along the positive x-axis. So that's positive 2k q2 divided by a squared. And since we're looking at the x component of this force at an angle, we need to bring trig into this. And so to make something an x component, you just multiply by the cosine of the angle, which in this case is 45 degrees because it's a square. Now for the field from charge 3 is positively charged, which means the direction looks like this, going to the top left. And we can see that the horizontal component from this force will be negative because it's pointing to the left. So this time we're going to do a minus 2k q3 divided by a squared. Still horizontal component, so we still multiply by the cosine of the angle. Now you might notice something kind of nifty. Notice that this term and this term both look the same, with the only difference being the q2 and the q3. But, as the problem is explained, both q2 and q3 have the exact same magnitude of charge, which means that this term and this term are both effectively equal. So we're subtracting one thing by the exact same thing. So they're just canceling out entirely, and this whole thing goes to 0. So the horizontal component, the x component of the net electric field, is 0. So we can just not even have to worry about the x component when writing our final answer. So that's cool. Now let's do the same thing for the y component. Now we can see from our diagram that the vertical component of both forces are going to be positive, because they're both pointing up. So there's going to be no subtraction in this formula, which unfortunately means nothing's going to cancel out here. But from charge 2, it's pointing upwards, so from charge 2, it's going to be 2k q2 divided by a squared multiplied by, and this time we're looking at the y component, so this time we're using the sine trig functions, the sine of 45 degrees, plus the contribution from charge 3, so 2k q3 divided by a squared times the sine of 45 degrees. If you want, you can simplify this a little bit by factoring out everything except for the charges. So that's 2k sine of 45 degrees divided by a squared, all multiplied by the magnitude of q2 plus the magnitude of q3. So now let's just start plugging values into our calculator. So that's 2 times the Coulomb constant, which is 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared, multiplied by the sine of 45 degrees, so make sure your calculator is in degree mode when you do this, divided by the square of a, which is given in the problem as 5 centimeters, or 0.05 meters, that's squared, and then multiplied by the sum of the two charges we made. And when I write q2 and q3, this is specifically as it pertains to our simplified diagram. So instead of using the problem's values that it gave us, we'll use the more simpler, smaller values of negative 10 nanocoulombs and positive 10 nanocoulombs. So this is 10 nanocoulombs, or 10 times 10 to the power of negative 9 coulombs, plus 10 nanocoulombs again, 10 times 10 to the power of negative 9 coulombs. And if we put all of this into a calculator, then we get about 101,710 newtons per coulomb, which can be more simply written as about 1.02 times 10 to the power of 5 nanocoulombs. And this is the y component of the net electric field. It is also the only component of the net electric field, because as we discussed earlier, the x component just disappears completely. So that means that in unit vector notation, the entire electric field at the center of the square can be written as 1.02 times 10 to the power of 5 newtons per coulomb. And since this is along the y-axis, we use the j-hat unit vector. So this is the electric field of the system at the center in unit vector notation. And that is it for this tricky problem. I hope this video helped you out. If it did, please consider subscribing or donating to my Patreon, as that'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below, and I hope you all have a lovely day. Bye-bye.